All right, welcome back. This is 4.2b, one sample means with the t-distribution, and we're going to be creating some confidence intervals today. So this might look familiar. It's a little bit different than what we've seen. I don't know why the sizing is always goofy on this, but there we go. So if we want to find a t-confidence interval for the mean, that is to say, it's very similar to finding the confidence interval for the mean, but using the z star. We're going to use the t star instead here because we're going to be using a t chart. So if we have, again, n independent and approximately normal observations, right? Then, and again, that approximate normal gets very loose with the t-chart, but a confidence interval is then, and again, this is what should look familiar. It's that mean, the sample mean, that x bar, right? Plus or minus the t star, and the t, this t star df is the, like the z star, it's that critical value that we were looking up at the chart. Based on df would be the degrees of freedom. So for example, if I have a let's say a t star of 10 degrees of freedom, you would see t star sub 10, right? And then that t star again just depends on the area that you are interested in pushing to the tail or the outside of the middle of your curve, right? So oh, and it says that z is the sample mean, or sorry, x bar is the sample mean, t star df corresponds to the confidence level and the degrees of freedom, and then se is that standard error as estimated by the sample, right? So we're going to take a look, and we'll go through one of these. Oh, I think we'll go through two, but let's look at some dolphins. Oh, you know what? I'll even get the picture because isn't that just so cute? All right, so we have these Rizzo dolphins. The question, the problem that they're stating here, we have dolphins. They're at the top of the oceanic food chain, which causes dangerous substances such as mercury to concentrate in their organs and muscles because they eat all the smaller stuff that has mercury and such in it. This is an important problem for both dolphins and other animals like humans who occasionally eat them. For instance, this is particularly relevant in Japan, where school meals have included dolphin at times. Right? So we want to why does it always do this? It's so obnoxious. Design a study and collect relevant data on the topic. So we're going to compute a confidence interval. That's the whole point of this, is to create that confidence interval for the average mercury content in dolphin muscle using a sample of 19 dolphins from the Taiji area in Japan, right? And so we are lucky that they've already kind of analyzed some data for us. Yoink. So the data is here. There were 19 dolphins surveyed. I don't know how they surveyed them. They might be dead, but there's 19 surveyed. They found that the average, this x bar, is 4.5, and not that it matters much, but this is milligrams, I want to say. I think it says micrograms. So micrograms just happens to use that same letter mu. In this case, it means micrograms of mercury per gram of muscle tissue before that tissue gets dried out. None of that's particularly relevant to us, plug of the numbers, but it might be relevant. In one study, if they dry the dolphin meat and then figure out how much mercury is in it, that's going to be a much different value than if you hadn't dried it out based on weight of whether the mussel had liquid in it or not. They calculated the sample standard deviation to be 1.9, and then we have a minimum value of 1.08, a maximum value of 7.68. So oops. We want to, let me leave this on the screen. We might need those numbers. We want to estimate the population mean, right? We've got a sample. Our sample mean is 4.5, but we want to create an interval for the population mean, right? But we also don't know the standard deviation. We have a sample standard deviation, so we're going to have to use that. And because we're using that, we're using a t-distribution, right? So where is it? There it is. All right, so we're going to do this. This resizing garbage is really driving me crazy. Sorry if it's driving you crazy as well, but we've got that X bar plus or minus a T star degrees of freedom times the standard error. So we need to figure out those values, right? So what they're asking us to do is, do they say what confidence value? No, they didn't. Here, let's calculate what we can first, and then they pose the question in a second. And again, if you aren't given your confidence level, you can typically then assume that it's 95%. So why is it got to do this every time? I don't know. So the sample mean and estimated standard error computed just in our early examples. We have those already. They were given to us. Your mean was 4.5. Your standard error is this formula here, that S that was above. Up there, 1.9. Oh, it's right here as well. So, oh, they did the math. Look at that. I don't have to do my math. So it's 1.9 divided by the square root of the n, that number of observations, which was 19. So they've calculated that. So we have this standard error is, I don't know if they rounded, but I'm sure they probably did, about 0.436. Okay. And then this value, the T star, right? We're looking for specifically in this case, it's T star of 18 degrees of freedom, right? And that star now is corresponding to 95% because it didn't ask us specifically to create better or worse interval than that, right? So we need the chart, which I will still here. And this chart that I'm copying and pasting here is on page 93, but it doesn't have all of the values. Obviously, it's missing 6 through 16 and 21 through 399. There is going to be one in the back of your book, but I also have one here. Yeah. So I don't know if you can see this very well. It's got some notes. I don't know what they'll say, but I will make a copy of this and bring that in. And so you can have this as well. So you don't have to flip around in an electronic book looking for it. But we are looking for see if I can get this on one page. I don't know. There. Good. All right, so we're looking for the degree, the T star that corresponds to 18 degrees of freedom, which is highlighted. Convenient. All right, so it's going to be one of these values. But again, since it didn't tell us our confidence level, we're going to assume 95. Which is our default unless otherwise, stated or requested, right? So that what we want to do is find the T value almost a good chart there, where the negative T star here and the T star here exclude in these tails a total, oh my God, get out of my way, of 5%. So if there's 5% stuck between two tails of this distribution, we assume that it's, fairly English just left my brain. The left side looks like the right side. I can't remember what that's called because I am going to die. I don't know. But the left side should have the same distribution as the right side-ish. So that means that in each one of these, we've got 2.5%. So I can either look at a one-tail test and look for 2.5%, or I can look at the two-tail and look for 5%. It doesn't really matter. You'll see that those numbers should be the same. So if I do a two-tail test, I want 5% outside those guys. And so that corresponds here to a t-value of 2.10. Likewise, if I looked at a one-tail test and went for 2.5, well, oh, look at that. It's the same column, right? So that means my t-star sub 18 in this case is 2.10. And so if I plug that up into, I'm going to scooch up and plug my values in here. My X bar, I don't know. Oh, it's 4.5. It's right there. It's 4.5. And then I have plus or minus that T star sub 18. That's 2.10. Or I can just omit the 0 because it doesn't matter. Times that standard error, which was calculated here at 0.436. Right. If I do the plus version of this, I get one number, right? And if I do the minus, I get a version of it, I get another number. Those two numbers are 3.58 is the lower value, and 5.42 is the upper value. Make sure you can calculate those. You'll need to do that. You'll need to be able to do that. But that gives us our 95% confidence interval. And so we would say this. Why do I just type? They changed the format. There it is. We are 95% confident that the mean, oh, that's not what I want, amount of mercury in whatever these dolphins are, I think they're Rizzo, is between 3.58 and 5.42 micrograms or blah, blah, blah. It doesn't matter, right? That's the interval, right? And you can also answer that in an actual interval form. You can say my interval is 3.58 to 5.42. right? And you can also say we're 95% confidence that the true mean lies in this interval and list it out, right? So that's our interval, right? We're 95% certain that it's in there. And these values are, I don't know what the acceptable value is, but what I do know is that 3.58 is too high. And that's the low end of our estimate, right? So we're 95% confident that our true mean of all dolphins out there and the Rizzo dolphins out there have an overall mean between those two values. That means that the average of every dolphin out there is too high, and we shouldn't be consuming them for any reason. Okay. The FDA's website provides some data on mercury content of fish based on a sample of 15 croaker whitefish in the Pacific. A simple mean and standard deviation were computed. Those values are 0.28 is the mean, and 0.69 is the sample standard deviation. Parts per million, respectively. The 15 observations ranged from 0.818, so we have a minimum value there. Oops. And we have a max value here. And then the question is not go ahead and do the same thing. The question is simply, if we assume that they're independent, because it's almost blatantly obvious that they are, because you only took 15 fish, and if that's more than 5% of the croaker fish, you should definitely not be fishing for them. But based on the summary statistics of the data, do you have any objections to the normality condition of the individual observations, right? And so what we'll do here is test to see how far out my minimum and my maximum go. If one of these is way off there, like 10 standard deviations away, I might have a problem with that. So I really just want to figure out how far out these guys are, right? Excuse me. Excuse me. All right. So I have a mean of 0.28. So if I take my minimum value and I go 0.18 minus that 0.287 and divide it by the sample standard deviation of 0.069, I get something, probably. I didn't do it, so I don't know. 0.287 all over 0.069. This is negative 1.55, or it's roughly that, about negative 1.55. And if I look at my max and do the same thing, I've got 0.41 minus 0.287 over 0.069. So that is 1.78-ish. So then, because these are within 2 standard deviations of the mean, I have no problem saying, yeah, this is almost certainly going to be normal, and I can use a t-distribution with this. Again, if I had gotten like a negative 10 or a positive 10 or something like that, something beyond, you know, I mean, if it's within 2, you're definitely safe. If it's outside of 2, you may have to, you know, be a little bit careful. But these guys, they're safe, right? They're within 2, so we can assume then that we have normal. Holy crap. All right. Estimate the standard error of the sample mean using the data summaries in guided practice 4.22. If we are to use the t-distribution to create a 90% confidence interval, so we now have a 90% confidence interval, then identify the degrees of freedom and also find t star df, right? So it's the same dolphin problem here. And so I still have, where did it go? I don't even know where it is. 4.5 is x bar, right? We've already calculated standard error. Somewhere. Oh, I'm just kidding. This is not that example. My bad. It's the example that we just talked about. I apologize. The mean, there we go. The mean is probably right above me. Nope, I deleted everything. All right, so my mean was in that example was 0.287. The sample standard deviation, S, was 0.069. And there was 15 fish. So N is 15, which tells us then that we can calculate the standard error. That standard error is S over square root of N. So that is 0.069 over the square root of 15. Okay. And that is approximately 0.0178. So there's our standard error. And then since N is 15, that then also, of course, corresponds to the degrees of freedom being 15 minus 1, so 14. Our confidence level is 90%. So if I go to find T star, it's T star sub 14, where the star now corresponds to 90%. So let me still this chart again. It's lovely that it resizes and reframes me every time. That doesn't drive me crazy at all. Well, that's helpful. 14 is not on this chart, so let me find the actual T chart in the back of the book. Somewhere. There's z-scores. There is T chart. Okay. Go away. Use up. There we go. All right, so 14 is on, and this chart is on page 193 in the actual book, in the ebook that we're using. So my degrees of freedom, where's my pen? Are 14. So I have 14 degrees of freedom. So I'm somewhere in there. We're talking about a 90% confidence interval. So once again, we're talking about keeping 90% of the values in here, which leaves us with a combined 10% on the outside. And so I can look for that 10% in a two-tail test, matching up with degrees of freedom being 14. So my T star is 1.76. I can create a confidence interval with this. It is my mean plus or minus that t star sub 14 multiplied by the standard error. So that is 0.287 plus or minus 1.76 multiplied by 0.0178. And that ends up being 0.256 to 0.318. That's not helpful. Okay. All right. And there we are. That is 4 point something, 4.2b. Yeah. Thank you. And I'll see you on the next one.